Hello everyone and welcome to another episode of Let's Code Duke Nukem, where we aim to recreate the original EGA action platformer, released in 1991. In the previous episode, we managed to convert some full-screen EGA data to actual images. In this episode, we will use a similar technique to convert the remaining graphics used by the game. The file format for these graphics are slightly different because it includes a fifth plane for transparency and it includes some dimensions and tile count. But converting the data to an image remain largely the same. Now, the good folks at the modding wiki have figured this stuff out for us, so we don't have to, and I'll include a link to the page in the description. All right, so here, these are the files we are looking to parse. So the animations, back tiles, backdrops, the border, everything, the font numbers. So it is the ProGraphx Toolbox tileset format. Now, it's used by several other games as well, but we are obviously interested in the Duke Nukem version of it. So here we go, image data. The image data is byte planar EGA format with 5 planes. So reading width times height times 5 bytes will read in enough memory for a single image. Oh, there we go, this is what we want. The first byte in each tile's data is the transparency plane. One is opaque. If the bit is set, then it's opaque. If the bit is not set, it's transparent. And the following 4 bits will be the things that we've seen already. So intensity, red, green, and blue. All right. So let's go to our IntelliJ IDE and let's just start by creating a function that returns a list, because each file will contain several tiles, so we'll convert them all to individual images. So I'll read tiles string name. Well, there we go. So the beginnings is going to be quite similar. We will let's first just create an empty list. And let's return it. Tiles, I guess we'll call it. Tiles. And let's also start with in is a new random access file, path.resolve. This is the same as earlier. Catch, if we do this too often, I'll make a shared function, throw new runtime exception, could not read name. There we go. All right, so the first byte is going to be the count, so the amount of tiles. So let's just call it count, and let's read the byte. Then we'll have the width in bytes, and then we'll have the height in pixels. Read the byte. And then it said that we could multiply the width in bytes times the height in pixels times 5, because we have 5 planes. And we'll do this per tile. So let's first make a loop. So here we'll make an array list that will be able to hold in all these tiles. For int go to the count. Let me just create a single read tile function here, where we take in the width in bytes, we take in the height in pixels, and let's just take in the file handle. This throws an IO exception. All right, so we have a buffer here. Data is a byte array of width times height times 5, right? All right, so let's read in these bytes. So we need to check if we reach the end of file. -1. If that happens, let's just throw an exception, unexpected end of a file. If we succeed, let's create the tile, new buffered image. And so the width, so each byte has room for 8 pixels. So we need to multiply the width in bytes times 8 to get the pixel count. The height is already in pixels. And this should be one tile. So we can return it here. And here, let's just go through all the bytes one by one until we reach the end. And let's not increment it, because we will increment it inside of the loop, because all the data is byte planar. So that means each byte represents planar data. So we need to increment it here. So let's take in the transparency, and here we'll do the same type of value of conversion that we did for the full screen in the previous episode. Sorry, data, and let's increment the counter. So we have intensity, reds, greens, red, green, blue plane, and then here we do the same bit loop. And we'll see if we can unify this with the other bit loop that we made earlier. But for now, the difference here is that we need to do a check for the transparency. So I guess we should call it opacity, because if it is set, then it's opaque. So let's just call this opacity. So if it's set, then we need to plot a pixel. So here we can just convert the index as we done earlier. So intensity.set bit, red test bit, green test bit. All right. Set RGB X, Y, EGA palette index. All right, we need to have int y equals 0, int x equals 0. Not set bit, test bit. Tile.set RGB. All right, and regardless, we need to increment the x pixel, and if we reach the edge here, tile get width, then we need to wrap to the next row. All right, so this reads an individual tile. So here we are looping the amount of tiles in this file. So we can just say tiles.add read tile with height in. And then this should convert all these images, all these tiles, into a list of images. All right, so let's give it a test here. So here we have our file, our main class here. So let's just take the numbers, for example. Yep, loader read tiles. Numbers it's called, right? Numbers. All right, so let's just go through each tile. And render them separately. Numbers get I. And then let's create a file name called number-plus-i+.png. So this will render out each individual sprite as an image. hopefully. So let's run it. All right, so here we have the numbers in the game. Okay, it's pretty cool. So let's do the same for, let's delete all this stuff here. I don't know, let's do object. What's it called? Object 0, for example. Object 0. And then let's call this object dash. Let's just see what it comes up with. All right. So here we have some graphics. There's a turkey. All right, so now that we can read in all the tiles, let's just quickly do the backdrop as well, because that is also tiles, but then they're laid out as a backdrop. And rather than rendering them as individual tiles, I think it's going to be handy if we can just create a single graphic that contains like just a single image that we can just render in one go. So let's create another function called buffered image read backdrop, string name. So here we have the same try catch thing here, which is unfortunate, I guess. So I think next episode we might just unify some of these things here. All right, so for the backdrop, the header can be skipped because we know exactly how many tiles we need to read and the size of each tile there. So the backdrop image is a bit smaller than full screen. It's 208 times 160, so it's like 13 by 10 tiles big. For int. So it's like 13 by 10 columns and rows, I mean. We could do just, okay, so for int row 0, row smaller than 10, for int column smaller than 13, and then we'll get the graphics of our backdrop and we'll draw the tile at the correct position. So we know the width in bytes is 2, and we know that the height in pixels has to be 16. Normally I would read this from the header, but the headers of these backdrop files are all set to 0, so we have to hard code it here. And yeah, we have the file here. And of course we need an X and Y position. So the X is col times 16 and the Y is row times 16. And we need to have an observer, but we'll set it to null. Now let's see if this works. So we confirm that the individual tiles work just fine. So let's delete them. And let's read one of the backdrops. So let's do drop 7. Resource loader, read backdrop, drop 7.dn1. Drop 7.png. All right, let's see if it works. Let's see if it works. Drop 7. There we go. We have a nice landscape here. All right, so now that we're able to read all the tiles, I think we have enough to actually start reading the levels so that we can draw the levels. but we'll do that in the next episode. For now, thank you very much for joining me. If you have any questions or if I did anything wrong, please let me know in the comments below. I'll see you guys later. Bye-bye.